Hello students, welcome to ePhysics. Students, as we were doing the question series for board exams, this is the second part of the first chapter of physics, that is electric charges and fields. So here in this video we will be discussing the questions related to the Gauss law. So let's start it now. The first question is on the screen, students. A hollow cylinder box of length 1 meter and area of cross-section 25 centimeters square is placed in a three-dimensional coordinate system. It is shown in the figure. Now, one thing is missing over here. This is the length of 1 meter and also the length of the cylinder is given, that is 1 meter. Okay, and the area of cross-sections of the cylinder's parts, that is this one and this one, each is equals to, it is 25 centimeter square, that is area is equals to 25 centimeter square. Now if we convert it into meter square, it becomes 25 into 10 to the power minus 4 meter square. We have to convert it for the SI units. Now it is given that electric field is given, it is equals to 50 xi. Xi means it is along the x-axis. Okay, now we have to find few things. One, we have to find the net flux, okay, through the cylinder, net flux through the cylinder. And the next thing, we have to find the charge enclosed by the cylinder. For net flux, students, we are saying we have two surface area. One is this one, the left part, and the right part, that is this one. Okay, now let us consider this is the right part, which let us name it as E, B, and this left part, let us name it as electric field along A direction. Okay, now this first part of the question says we have to find the net flux through the cylinder. So when we move on solving it, we have been knowing that EA will be equal to 50 multiplied by, this is in the left side, EA is along the left side, and which is from the origin is at a distance of 1 meter only, so will be equal to 1 Newton per Coulomb. So finally we can write it as 50 Newton per Coulomb. Okay, now for the magnitude of electric field along the right face, that is EP, is equals to 50 multiplied by, this face is at a distance of 1 plus 1, that is 2 meter, Newton per Coulomb, which is equals to 100 Newton per Coulomb. Okay, now for the corresponding flux, corresponding means for the flux along the surface area A, let us consider it is phi A is equals to EA into the area of cross section. Okay, area of cross section, we have been knowing that it is equals to 25 into 10 to the power minus 4 meter square. So this can be written as 50 multiplied by 25, okay, multiplied by 10 to the power minus 4 into cos theta. Here when we are talking about this side, this is opposite to the direction of the electric field, therefore this angle is equals to 180 degree. So we will have to write it is equals to cos 180 degree. So finally we will get it is equals to minus of 0.125 Newton meter square per Coulomb. So this is along A. Now the flux along B, that is phi B, is equals to EB dot delta S is equals to, we have found it as 100 into the same thing, 25 into 10 to the power minus 4 into cos. Now here, since the electric field is also in this direction and the area vector along this face B is also in this direction, therefore the angle here becomes 0 degree. So we will be writing it is equals to 0 degree, and here we get it is equals to 0.25 into, sorry, not into, it is Newton meter square per coulomb. Okay, now for net flux, we were supposed to be finding net flux. Okay, for net flux, that is phi is equals to phi flux along surface area A and flux along surface area B, which is equals to 0.125. This is negative of 0.125 plus 0.25. Let us make it as 0. Okay, and overall the unit is equals to Newton meter square per coulomb, which is equals to 0.125 Newton meter square per coulomb. So this is the net flux. Now the second part of the question says charge enclosed by the cylinder is also needed to be found. Now when we are talking about the cylindrical surface, we talk about the closed surface. Okay, closed surface in which the flux is being linked. So whenever we talk about the closed surface, we have to use the Gauss's law. Okay, Gauss's law. The Gauss's law has been discussed in the video. You can check it in the channel. That the link will be provided in the pinned comment. Okay, now here the Gauss's law says that net electric flux, that is E dot ds, is equals to 1 upon epsilon naught times the charge linked to it. Okay, now the net flux is already been found over here, that is equals to 0.125 equals to charge we have to find, and epsilon naught's value we know it, it is a constant, that is 8.85 into 10 to the power minus 12. So the charge will be equal to 1.1 into 10 to the power minus 12 coulomb. After calculation, this is the charge that we find it. Okay, so this is how we solve the kind of questions. Okay, the question is on the screen, and also this is the process how we will be writing the answer in the board exams. So the annotated PDF will be provided from the link in the Telegram. Okay, so no need to write it, just watch the video and try to understand the process through which we will be writing the answers in the board exams. Let's move to the next question. The next question is on the screen, students. A uniformly charged conducting sphere. Okay, we have to keep in mind that we are talking about sphere of 2.4 meter in diameter. If the diameter is equals to 2.4 meter, then the radius will be equal to 2.4 divided by 2 meters, which is equals to 1.2 meters. Okay. Also, the charge density has been given. The charge density is equals to, that is sigma is equals to 80 microcoulomb. Micro means 10 to the power minus 6. Okay, coulomb per meter square. Okay, these are the things which have been given. So the first part of the question says find the charge on the surface. So for finding the charge, we know the formula of the surface charge density, that sigma is equals to charge upon area. Now since we are talking about the sphere, let's write it first. 80 into 10 to the power minus 6 equals to Q divided by the area of the sphere, and the area of the sphere is 4 pi r square. Okay, now when we put the values over here, when we put the values, we get, that is charge is equals to 80 into 10 to the power minus 6 multiplied by 4. This whole part will move over here and will be multiplied, and it becomes 4 into pi. Pi ka value is 3.14 into r square. R square, that is 1.2 ka whole square. So which can write it as 1.2 multiplied by 1.2 coulomb. So it is equals to, after calculation, we get it as 1.48 into 10 to the power minus 3 coulomb. So this is the first part of the question. Now let's move to the second part. It says, what is the total electric flux leaving the surface of the sphere? Total electric flux. So for flux, we know the formula, that is flux is equals to charge upon epsilon naught. So flux equals to charge, we have just found it. It is equals to 1.48 into 10 to the power, how much? It is minus of 3. So it is equals to minus of 3 divided by epsilon naught. We have been knowing the value of epsilon naught. It is a constant, that is 8.85 into 10 to the power minus 12. Okay. Now the unit of the flux is Newton meter square per coulomb. So after calculation, we get it. It is equals to 1.63 into 10 to the power 8 Newton meter square per coulomb. So this is how we solve these kind of questions. Okay. Now let's move to the next question now. Now the next question is again on the screen, students. The two large parallel thin metallic plates. We have two plates, remember it, two plates, okay, close to each other. The plates have surface charge density of opposite sides. Two plates and the surface charge density are of opposite sides. It means if one of the plate is having the positive surface charge density, then the other will be having the negative surface charge density. Okay, if one has the positive one, then other will have the negative one. Now it is given the magnitude of the densities are 2.0 into 10 to the power minus 12 coulomb per meter square. So the first part says calculate the electric field intensity in the outer region of the plates. For the outer region, let us consider we have two plates. Okay, one is positive surface charge density and the other is of negative surface charge density, and let us consider the distance between them is r. Okay, now let us consider the charge. Okay, now here we have to calculate the outer region of the plates. So let us consider we have a point P outside the plates. Okay, point P outside the plate, and the electric field will be from the positive to the negative charge. So this is the direction of the electric field. Okay, for E, let us consider this is E1, that is along the direction of the electric field, and let us consider this is E2, that is opposite to the direction of the electric field. Okay, and surface charge density for both the plates have been given, that is 2 into 10 to the power minus 12 coulomb per meter square. Okay, this has been given. For E1, we can write it as, this is the part 1 of the question. For E1, we can write it as sigma upon 2 epsilon naught. This is according to the formula r cap. R cap denotes the direction from positive to negative. Okay, and for E2, we can write it as, these are the vectors. Okay, these are the vectors. So sigma upon 2 epsilon naught r cap, but this is on the opposite direction, therefore we will be putting the negative sign in front of it. Now therefore we can find the net field, net electric field outside the surface. E will be equal to E1 plus E2. Okay, we can clearly see both E1 and E2 have the same magnitude, but the directions are opposite, therefore it is equals to 0. So this is how we solve the first part of the question. Now the second part of the question says, in the interior region between the plates, what will be the electric field? So for second part, we have to find in the interior region. We have been knowing that E1 is equals to sigma upon 2 epsilon naught. Okay, and this is r cap, of course, yes, and E2 is equals to sigma upon, this is sigma upon 2 epsilon naught r cap. But here we will be talking about the magnitude. Why only the magnitude? Or even if we don't take the magnitude, okay, even if we don't take the magnitude, what happens when we are talking about the within the plates, when we are talking with about the charge or the point within the plate, we don't need to take the direction. Okay, now here the net electric field will be equal to E1 plus E2, which can be written as sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. So half of sigma upon epsilon naught plus half of sigma upon epsilon naught is equals to, this is r cap for both, okay, is equals to sigma upon epsilon naught 1, okay, and r cap as the direction. Since it is from the positive to negative plate, we got the positive sign over here. We have been knowing the value of sigma, that is 2 into 10 to the power minus 2 coulomb per meter square. Therefore, electric field is equals to sigma ka value is 2 into 10 to the power minus 2, okay, divided by epsilon naught. Epsilon naught ka value also we have been knowing, that is 8.85 into 10 to the power minus 12, okay, coulomb Newton per coulomb, okay, which after solving it, we get it as 2.25 into 10 to the power minus 1 Newton per coulomb. So this is how we solve these kind of questions. Now next, move to the next question now. Now the next question is in the screen. A uniform electric field E is equals to EXI Newton per coulomb for x greater than 0, and E is equals to minus of EXI Newton per coulomb. I means the electric field is along the x-axis, but one is in the positive direction and other is in the negative direction. The positive direction, the value of x is greater than 0, and for the negative direction, the value of x is less than 0. And we are talking about a right circular cylinder, okay, of length L centimeter. So let's make the right circular cylinder first. So this is the right circular cylinder, okay, of length L units. Now, and the radius of the cross section has been given, that is equals to r centimeter from its center at the origin and its axis along the x-axis. So it is axis along the x-axis. Now its center is at the origin. So this is the three-dimensional shape. This is the x-axis, this is the y-axis, and this is the z-axis. And when we talk about the electric field, one will be along the right hand side, along the positive x-axis. Let us consider this is E for R, that is the right hand side. The other will be along the left hand side, that is the negative of E. Let us consider this is EL, and the other will be perpendicular to the surface, okay, perpendicular to the surface. This is 90 degree. Here cos 90 is equals to 0, so we don't have to consider this part, okay, we don't have to consider this part. Now we will be considering the right hand side and the left hand side only. So now when we talk about the electric flux, total flux, that is phi, it is equals to phi along the right hand side and the flux along the left hand side as well. The flux along the right hand side will be equal to Ex, okay, Ex for the both sides, it has been given Ex, okay, and multiplied by area. The area of cylinder, the cylinder's cross section is circular in shape, therefore it will be pi r square, and the radius was given in centimeter, so we have to convert it into meter. Therefore this becomes 10 to the power minus 4, okay, plus Ex, and for the left hand side also Ex, and it will be written as, pi r square into 10 to the power minus 4. Now students, for the right hand side we have considered it as r, so we will be writing it er. For the left hand side we have considered it as l, so we will be writing it as el. Now since both the magnitudes are same, so el and er can be written as ex. Okay, this is also ex, this is also ex. And pi r square is common in both, so we can write it as pi r square is common in both, and also 10 to the power minus 4 is also common, so we can also write it as 10 to the power minus 4 as common. So 1 plus 1 becomes 2, so we can simply multiply it by 2. So this is the value, and total flux ka unit is Newton meter square per coulomb. So this is the total flux linked to the cylindrical surface. So the net charge, since we are talking about the closed surface, we will be using the Gauss's law. So by Gauss's law, we have been knowing total flux linked is equals to 1 by epsilon naught times the charge. Okay, now flux we have found it, therefore charge is equal to flux multiplied by epsilon naught, where flux we have found it to Ex, this is E, x pi r square into 10 to the power minus 4 into epsilon naught. When we put it, this is coulomb because we are talking about charge. When we put the values here, we will find it. So this is how we solve these kind of questions. Now, these are the process, students, how you will be attempting the question in the board exams for the numericals, and one question will be given as your homework. So please try to solve it. In the derivation part, you will be learning, or you might have studied the Gauss's law and the applications of it. So this question you will be able to solve it from the derivation part of the Gauss's law, from the applications of the Gauss's law. So I hope you understood the video very well. The PDF, this solution with the solution will be provided in the Telegram channel, and the link will be provided in the description. So hope you understood it. Thank you very much for watching the video.